All right, in this video, we're going to take a look at a differential equation which gives us something we call the logistic model for population growth. This type of model arises in a certain scenario, but I don't want to tell you yet what that is. So instead, let's start with the equation, and then we're going to work through a few scenarios. We'll do a little bit more analysis. Then we're going to sketch the slope field for this differential equation that will allow us to visualize what solutions to this differential equation would look like. After that, we will solve it using separation of variables. We'll do a little long-term analysis to verify the behavior that we see in the slope field, and then I'm going to numerically plot some trajectories for you. Okay, so let P of t represent a population at time t that satisfies this equation, dp dt equals r times p times the quantity 1 minus p divided by k. Here, r and k are parameters greater than 0. And whereas mathematically you could find a solution to this differential equation, which is negative, since we're talking about population, we're going to assume that our starting population, p of 0, which I'll denote by p naught, is greater than or equal to 0. All right, so in this differential equation, our independent variable is time, t. Our dependent variable is p, population depends on time. If you look at the parameter r out here, you could think of r as scaling the rest of the equation. So it's like r times these expressions in p. So r is a parameter that allows you to scale the growth rate. That would depend on your population and the ecosystem. K down here is a little bit more mysterious, so let's work through a few scenarios. So first, what if the population is 0? Well, this first term would be 0, so we'd have 0 times something, 0 times 1 actually. So dp dt would be 0. This is an autonomous differential equation. It has no direct t dependence. So the derivative would never change because of t, and then p is stuck at 0, so our population would be 0 for all time. In other words, if we don't have any rabbits, we're never going to have rabbits. So this is an equilibrium solution. Something interesting happens also if p equals k. If you plug in k for p, then p over k is 1, so this whole second term becomes 0. So we'd have r times k times 0, which means the derivative is also 0. dp dt when p is k is 0, and again, that's another equilibrium solution. Regardless of time, if the population is k, we're not going to change. Okay, what if the population is between 0 and k, so p is less than k? Then p over k is less than 1. So 1 minus p over k is greater than 0. So you subtract that to the other side. And I'm not going to take it much further right now. R is positive, p is positive, and this third term would now be positive. So the only thing I'm going to say is qualitatively we know that our population will be increasing. So dp dt would be positive. We'll break that down a little bit more in a second. On the flip side, if p is greater than k, then 1 minus p over k is going to be negative. It's the opposite of the situation we just looked at, so p over k would be greater than 1. So that means you would have positive times negative, or in other words, the derivative dp dt would be less than 0. So if our population is greater than k, the population will decrease. Okay, I think these are the 4 major behaviors to observe when you look at this differential equation the first time, but we can take it a little bit further, so let's add some nuance. So what if p is much, much less than k? So this is a bit vague here, but I'm saying imagine that p is really small, like maybe k is 100 and p is 5 or something like that. If that's the case, then the ratio p over k is approximately 0. Or I guess what we could say perhaps better is that it's much, much less than 1, which means that 1 minus that is approximately 1. It's a little bit less than 1, but not by much, which means that our differential equation is roughly r times p times 1. So it's about r times p. Which means if you looked at a very small population, say k was much larger, you might expect to see exponential growth, at least while the population remains much smaller than k. That will change as soon as we can't really say that 1 minus p over k is approximately 1, but we would be near exponential for a small population value. On the flip side, if p is approximately k, then p over k is approximately 1, which means that 1 minus that ratio is approximately 0. So our population's rate of change near k is approximately 0. I don't know if you enjoy this kind of murky analysis where you're approximating behaviors, but I think it is handy when we put together the slope field. We have one more piece of evidence to look at before we start visualizing what solutions to this differential equation are going to look like. And this is kind of neat. Let's compute the second derivative for this population. So I would like to compute p double prime of t, where p prime of t, or dp dt, is our given equation rp times the quantity 1 minus p over k. Okay, so let's differentiate both sides of this equation with respect to t. On the left, I'm going to get our desired second derivative, and on the right, I'm going to use the product rule and realize that the derivative of p is p prime. So we have rp prime times 1 minus p over k, and then plus rp times, and that's going to be negative p prime over k. So let's simplify this as much as possible. There are different ways you could proceed algebraically here. You could just expand everything and then look for like terms or cancellations. What I'm going to do is pull rp prime out of both of these terms. So let's have rp prime times 1 minus p over k minus p over k. Okay, so obviously we can do that last part as 1 minus 2p over k, but additionally, let's take the p prime here and replace it with the whole right-hand side that we started with, because that's what dp dt is. So I can write r times the quantity rp times 1 minus p over k. So that is p prime, and then times 1 minus 2p over k. So just to rewrite it cleanly one more time, that's r squared p times 1 minus p over k times 1 minus 2p over k. I think it's best to leave it like this in factored form, because if we want to study the concavity of the population to understand the shape the solution curves are going to take, we actually want to look for inflection points and then the sign between the inflection points. Now, inflection points are when the second derivative is 0. So you want to find the zeros, and that's usually easier to do if a polynomial is in factored form instead of expanded. Okay, so here's our number line. And we're going to have that the second derivative is 0 when p equals 0. From this middle term, that's 0 when p equals k. And for the third term, that's 0 when 1 equals 2p over k, or in other words, p is k over 2. So let's order them as 0, k over 2, and k. Those are our 3 inflection points. We said that this is for populations, so we want to think of our populations as greater than or equal to 0. But just for fun, let's figure out the concavity to the left of 0. Since the second derivative is written in factored form, I just need to know the sign of each of the factors, and then the product of their signs gives me the overall sign of the second derivative. So if p is negative, that first factor, r squared p, is negative. The second one would be positive, and the third one would also be positive, because we'd have minus a negative. So overall, this is negative. That's concave down. And that is actually enough to figure out the rest of them because this is a cubic, but let's go through it anyway. If p is just bigger than 0, that first term switches to positive. Imagine p very small, positive, almost 0. The middle term is also positive, and the third term is also positive. In other words, by crossing from here to here, we only flip the sign of that first expression there. So overall, their product is positive. On the other hand, between k over 2 and k, we flip the sign of this third factor. So we're going to have positive, positive, negative, so that overall the second derivative is negative between those second two inflection points. And then when we are greater than k, the middle sign flips so that it's positive, negative, negative. The overall product is positive. Now, when I said that you could have figured that all out right away, it's because this is cubic. If you look at the highest term, it's p times a negative p over k times a negative 2p over k. That's a positive leading cubic coefficient. So you can determine what the end behavior would have to be. You have 3 distinct roots. So the second derivative would have to have the form like this as a cubic. Okay, so by analyzing the sign of the second derivative, we can figure out the concavity of these solutions. It's concave down smaller than 0, whatever that means. Again, we're talking about populations here. Then it's concave up between 0 and the middle inflection point, concave down between the middle inflection point and k, and then concave up again. Okay, let's see if we can piece together everything we've done so far to sketch a slope field. Okay, so first let's put in some axes. Our independent axis is for time, our dependent one is for the population. I don't have a specific value of k, but let's just put it somewhere on the y-axis, or the p-axis rather. How about there? And then we can also add k over 2 because we know that's an inflection point. Okay, a couple of remarks I'm going to add to the left of the p-axis. We are concave down for negative population values, concave up, and concave down again, and then concave up. We also learned at the very beginning that we have 2 equilibrium solutions. There were no others for this quadratic. If p is less than k, our derivative is positive. If p is greater than k, it's negative, so we know where the population is increasing and decreasing. Also, might as well mention that if the population were negative, the derivative would be negative, so we can add that. So let me add to this, p prime is less than 0, and this whole region here, p prime is greater than 0, and then p prime is less than 0. Okay, let's add those equilibrium solutions at 0 and k. So if the population is k, it stays there forever. Likewise, if it's 0, it's a little bit harder to see, but you can also just keep in mind the t-axis is an equilibrium solution. Now thinking of the second derivative as the derivative of the first derivative, that means k over 2 is a critical point, and in fact, it's a local max for dp dt. The actual value, if you plug in k over 2, the k's cancel out, and you're left with rp over 2. It's hard to say what that is without knowing what r is. In fact, it's impossible. So let me associate to that a value. I'm going to make it look like slope 1. It's hard to draw these totally consistent, so I'm going to copy paste. Near k, we're approximately 0. So I'm going to do something like that. And then copy paste. Also, when p is about 0, we're approximately 0. So let me do the same bar down at the bottom. I actually think I'm trying to squeeze too much in here. Let me just do one more. So I'm going to move these. So between these slopes and these slopes, I want to draw a nice change. So from here, we're slightly positive. Here, we're the most positive we get. So something between the two. Okay, I think that's a pretty good slope field between 0 and k. Above k, p prime is negative, so all of our little slope segments are going to point down. Near k, it's approximately 0 again, and then as p grows and grows, this first term grows larger, is a larger positive number. The second one is a larger negative number, if you will, further to the left. So the slopes get steeper and steeper as we go up and up. So let me just add in a couple pieces up there. On the other hand, if p were negative, if it's just below 0, the derivative is approximately 0, and then we see the reverse behavior that we just sketched. The more negative it gets, the larger in size these two terms get, so the product becomes an increasingly negative number. So I'm going to just kind of reverse the slopes I just drew. All right, so there's our slope field. This was done by hand with a lot of copy pasting, which is an advantage of working on an iPad. If you're doing this by hand, totally on paper, you might not catch so many little slopes. If you have computer software that can do this for you, you can also use that or at least assist yourself with that. Let me now imagine that I drop a population somewhere on this field and I allow these slopes to kind of steer me to see how the population changes over time. First, if the population is 0, it should stay at 0. We don't spontaneously have a population. Likewise, if it starts on k, it's going to stay at k. I think I'm going to leave those as dashed lines. Now, if I start with a very small population, I'm going to grow like this and then kind of turn and bend like that. Let me try that again. I'm not totally happy with this. Okay, I don't know if that's really better, but there we go. Let me start with a slightly larger population. Could look like that. Let me start with a population which is greater than k. And I'm flattening these out and approaching k because we shouldn't cross that equilibrium. Let me sketch that again. Now, in reality, a real population might not behave exactly like this, but mathematically, this is what solutions to our differential equation should do. And if for some reason we had a negative population or this differential equation modeled something that could be negative, it would go like that. Okay, let's think in terms of concavity now for the solution curves that I've just sketched. I did the best I could, and notice that between 0 and k over 2, my solution curve here for that first one I drew is concave up. After k over 2, it's concave down. Above k, it's concave up. And below 0, it's concave down. So that's where you can see the concavity information. Qualitatively, what happens to these populations over time? And for that question, let's only consider the populations which are greater than 0. If our population is small, or say anywhere less than k, it could start out just under k like this. Then our population grows to approach the equilibrium solution that we have at k. If it is k, it's just already at k, it stays at k. If it's larger than k, then it decreases down towards k. K is the destination. We call this the carrying capacity for the logistic model. So the logistic model is in a lot of ways more realistic than the exponential model for growth. What it says is that within some region, you might see something which looks kind of like exponential growth. So if k is a large number and p is much, much smaller, you might observe exponential growth, but only for a while. Ultimately, because of, say, limited resources, your population can't have exponential growth forever. And in fact, if the population is too large, say it's larger than k, it's exceeding the carrying capacity of its ecosystem, the population is going to have to decrease so that long term, these populations stable at the carrying capacity k. Okay, now that we put that picture together, let's go ahead and actually solve this differential equation by hand. We're going to use the separation of variables technique. It is separable. And along the way, we'll encounter some partial fractions. So we recognize that this equation is separable. So what I'm going to do is start to rearrange the terms. But before I rearrange the terms, let me make a nice adjustment. You might not see to do this, but there's a trick with the logistic equation. Let's multiply the left and right sides by the number k. So on the left-hand side, we have k dp dt, and on the right-hand side, we have rp times 1 minus p over k times k. I'm going to distribute that k so that we can write rp times k minus p, and that's going to just make things a little cleaner. So now let's put the p terms on the left. I'll leave r where it is on the right. In order to use separation of variables, I'm going to write this as the integral of k divided by p times k minus p dp, and set that equal to the integral of the constant r dt. Let's go ahead and integrate the right-hand side. That's just a constant integrated with respect to t. That's going to be rt plus a constant. I'm going to call it c1. To integrate the left-hand side, we're going to use partial fractions. I'm going to take the expression k divided by p times k minus p and write it as some numerator divided by the first term p in the denominator plus another numerator divided by k minus p. That's the kind of decomposition we want. Let's now add those two fractions together. Using a common denominator, across the top I'm going to write ak minus ap and then plus bp. That's all over p times k minus p. Comparing numerators now, we can say ak minus a minus b p, I just did a little factoring there on the left, equals 1k plus 0. So I did a lot there, but what it amounts to is this numerator, ak minus ap plus bp, equals the other numerator, which is k. So the ak is just as it is, and then minus ap plus bp, I chose to pull out the negative, that was optional, leaving me with a minus b, and then that expression times p. On the right-hand side, k is just k. Because I want to compare the coefficient of k, I put 1 there just so that we match up the a. And then I meant to add plus 0p. Comparing similar terms now, I'm going to compare ak to 1k and a minus bp, negative a minus bp, to plus 0p. The first pairing tells me that a equals 1, and the second pairing tells me that a minus b is 0. In other words, b and a are the same. So b equals a, which equals 1. So this decomposition was not too bad. We get that k divided by p times k minus p can be broken apart into two separate fractions as 1 over p plus 1 over k minus p. You can check your work now by trying to add these two together with the common denominator. You would get 1 times k minus p plus p, which leaves you with just k. Let's now integrate the left-hand side. I'm going to ignore the right-hand side for a second, so let's just focus on the left-hand side. Okay, so I'm going to say the integral of k divided by p times k minus p with respect to p is now the integral of 1 over p plus the integral of 1 over k minus p dp. Let me keep writing across the right. So that's going to be natural log of the absolute value of p plus natural log of the absolute value of k minus p. But you have to be careful there, because if you were to differentiate this, it would be 1 over k minus p times negative 1 because of the chain rule. So this negative right here means that the sign actually should have been negative. So it's natural log of p minus natural log of k minus p. There's another trick we use to write a clean version of the solution for the logistic equation. We already saw one, which was multiplying both sides of this equation by k. The second trick is to factor out a negative 1 here and write this as natural log of the absolute value of k minus p minus natural log of p. And then using a property of natural log, that becomes the natural log of k minus p divided by p. I didn't write a constant of integration here because we already picked up a general one when we did the right-hand side. Let's now take the left-hand side and set it equal to the right-hand side, and we'll start to simplify. So where we left off, we had negative natural log of the absolute value of k minus p divided by p equals rt plus some constant, which I'm calling c1. I'm now going to multiply both sides of this equation by -1, essentially transferring this negative to the other side. I'm also going to take this fraction here and write this as k over p minus 1. So now this is going to be the natural log of the absolute value of k divided by p minus 1 equals negative rt, and then I'm going to write plus c2 with the understanding that c2 is negative c1. It's just another constant. This is as simple as I want to make it, so let's exponentiate the left and right-hand sides. On the left, we're doing e to a natural log, so that leaves us with the absolute value of k divided by p minus 1. And on the right, we have e to the negative rt plus c2, which is e to the negative rt times e to the c2. In order to remove the absolute values, I'm going to take e to the c2 and replace this with a general constant, which could be positive or negative, so that we're absorbing the sign. So on the left, I'm going to write k divided by p minus 1, and on the right, d e to the negative rt, where here we note that d is plus or minus e to the c2, and the plus minus is to remove the absolute values. Continuing on, let's write this as k over p equals 1 plus d e to the negative rt. I can now isolate p. P is k divided by 1 plus d e to the negative rt. It looks like we're done, but we're not, because we want to take d now and replace it with something more specific that tells us information about the initial population. So let's see what that information needs to look like. If I plug t equals 0 into the left-hand side, I get the initial population, and when I plug it into the right-hand side, I get k divided by 1 plus d e to the 0, which is just k divided by 1 plus d. Let's solve for d now. This tells us that 1 plus d is k times the initial population. So we can replace that constant d with k divided by p naught minus 1, which I'm going to write as k minus the initial population divided by the initial population. Okay, let's make that replacement now in our solution. We have p equals k divided by 1 plus k minus p naught divided by p naught e to the negative rt. Multiply this by p naught divided by p naught, and we get k times the initial population divided by the initial population plus the term k minus p naught, all times e to the negative rt. This is how we find the general form of the solution to the logistic equation. So now we know the starting differential equation has a solution that has this form. Let's check two special values of the population. If the population is 0, then we get 0 divided by k e to the negative rt, so that's just 0. Whereas if the initial population is k, we get k squared divided by k plus 0, which is just k. So this form of the solution also works for those two special equilibrium solutions. Let's see if our solution matches the long-term behavior that we predicted from the slope field. So what happens as time t goes to infinity? The only place we see t is down here in this exponential term in the denominator. As t goes to infinity, e to the negative rt goes to 0. So the limit of our population goes to k times the initial population divided by the initial population. So it goes to the carrying capacity. That matches the behavior that we saw in the slope field. Lastly, I'd like to show you what a few trajectories of solutions to this differential equation look like in MATLAB. This concludes our discussion of the logistic equation. Thank you for your attention.